Continue with chapter 4. Section 2 deals with a concept called the mean value theorem. What the mean value theorem is used to prove is that two different functions can have the same derivative. For example, we know that if y equals 2, the derivative is 0. The question is there another function is there another y whose derivative is equal to 0? So if two functions have the same derivative, how are they related? How are two functions related if they have the same derivative? That's what the mean value theorem hopes to prove. But in order to get there, we first have to discuss something called Rolle's theorem. Rolle's theorem says this. Suppose f of x is continuous over some closed interval. And differentiable at every point of its interior. Okay, so it's continuous. It means that there's no breaks anywhere in there from the endpoints and every point and differentiable at every point, meaning the first derivative exists at every point inside the intervals, inside the interval. And then we can't look at the endpoints because, again, with respect to the limits, we can only take one-sided limits there. So if this is all true, if f of a equals f of b, then there is at least one number C on the interior with first derivative equals 0. If f of a equals f of b, if f of a equals f of b, there's a horizontal line there, then there's at least one point in there where the derivative is equal to 0. Meaning we have a horizontal slope there. Good. Concept says at least one point. What if it's a fourth order equation? So we can have point A is here. And point B is here. So it's a closed interval. Function's continuous. It's differentiable. There's a derivative exists at every interior point between A and B. Then there's at least one C. There's at least one C inside that interval where the derivative is equal to 0. So the derivative at C1 equals the derivative at C2, which is the derivative at C3, which all equals 0. They're all horizontal lines. That's what Rolle's theorem says. Because remember, as long as f of A equals f of B, as soon as if we drew a line, these endpoints connect. Then therefore there's at least one zero slope in there. Because that's what's going to lead us to our defining what the mean value theorem says. Remember, it has to be continuous. There are three examples that I gave you all in our packet. What if this is A and this is B? They equal each other, but it's not a continuous. It's a jump discontinuity in this one. So that's discontinuous. Here's A and here's B. F of A equals F of B, but it's not continuous. So it's not differentiable at every point inside there. And you can't have points either. So F of A equals F of B. That's why it's important to have the conditions have to be met. It has to be continuous inside A between A and B. It has to be differentiable at every point within the interior of AB. So let's look at example 1. It says, show that the function f of x equals x cubed plus 3x plus 1 has exactly one real solution. So let's show how this one. So we set our equation equal to 0. Remember, when we talk about real solutions, we're talking about the x-intercepts. All right, so that's how we find the solutions. So to prove that it has exactly one real solution, we find the derivative. We set the derivative equal to 0. And we solve for x. we see that this equation is impossible because x squared can never be negative to make it 0. So it will be never equal to 0. In other words, this equation's always greater than 0. So therefore, it cannot have more than 1 0. This is an increasing function. So that's what that says. Again, it's not looking for a specific number, it's looking for the concept. Since it's an increasing function, it can only have at most 1 0 because it can never go back down. That brings us now to the mean value theorem. What the mean value theorem does, it guarantees that there exists a point where the tangent line to a curve is parallel to the secant line connecting points A and B. So the mean value theorem guarantees that there's a point where the tangent line to a curve is parallel to the secant line. So let's look what that means. Here we have A, so there's point A. Here we have B, so there's point B. The secant line connects points A and B. Because of the secant line, we talked about this earlier when we talked about the limit function. As h, which is the distance between these two, as h goes to 0, we could find the point tangent to the curve that has the same slope as the secant line. As in other words, take the secant line, as h goes to 0, we'll have a line that has the same slope, but is tangent to the curve. So that's what the mean value theorem tells us. If we have a secant line, then there's a parallel tangent line to that curve. The mean value, here's a theorem. Suppose f of x is continuous over the entire closed domain AB and differentiable on every interior point in the open interval AB. Because interior points cannot include the outside points. So suppose f is continuous on the closed interval and differentiable at every point. There exists at least one point C contained in that open interval. It's an interior point C. At least one interior point C where f of A or f of B minus f of A over B minus A equals the derivative at that point. Have we seen this before? My examples. Have we seen this formula before? Yeah. This is the difference quotient. We took limits of it as h goes to 0. This is h. This is the slope. The derivative is a slope. So the secant line has the same slope as the tangent line, which means they're parallel. Okay, let's look at example 2. The function f of x equals x squared in the figure below is continuous for every x between, so that's the closed interval. And differentiable for every x inside that interior point. We use the mean value theorem to find a value C in 0, 2. Such that f of B minus f of A, B minus A equals f prime at C. So how do we do this? Well, we have to use this. We're looking for that value there. So what are A and B? Yeah, it's the closed interval AB, which is 0, 2. This is A, and that's B. Do we know what f of B and f of A are? What's the function? So do do we have f of b, f of a? What are they? Because b is 2. 2 squared is 4. A is 0. We have 4 minus 0, 2 minus 0. The first derivative is 2x. Actually, 2c in this case. So we have 4 divided by 2 equals 2c. 2 equals 2c. C equals 1. Is that a valid answer? Why? Is what? It's inside the domain. Yeah, it's between, and so that means both of these slopes are the same. The slopes are the same only when x equals 1. So if we look at the graph of this thing, x squared looks like this. So when x is 1, y is 1. When x is 2, y is 4. So the slope here is 2. No, it's 0. I'm sorry, the 0. The slope of that line is 2. At 1, the slope of that tangent line equals 2 as well. So these two lines are parallel, which is what the mean value theorem tells us. Put it back. Look at the very top of it. Because I'm looking for the first derivative at c. I'm looking for the value of c. So the function would be f of c equals c squared. I'm looking for the value of c. You can call it anything you want to. I can call it horse if I want to. It's just that since I'm solving for the value of c, that's what I'm looking for. Let's look at example 3. If a car accelerates from 0 accelerating from 0 takes 8 seconds to go 352 feet. What is its average velocity? Its average velocity is, and then 2, use the mean value theorem to determine that somewhere during the acceleration process, This, the speedometer shows the same value. Four. So how you do this one? If a car accelerates from accelerating from zero, takes 8 seconds to go 352, what is its average velocity? Hmm? What does average mean? Do we have a formula that shows us an average? Did we just talk about one in the last 5 minutes? Yeah, the slope equation. F of B minus F of A, B minus A. That's the average velocity or average speed or whatever it's average. It's the average because it's the y's over the x's. So what is F of B? What is F of A? What is A? And what is B? And what is A? A is 0, F of A is 0. Eight, and it goes 352 feet, right? The time is always the X, the input. So this is the input. So we have 352 minus 0 over 8 minus 0, which gives us what? So we have 2 goes in there. 176 over 4. 2 is in there. 88 over 2. 44. So it goes 44 feet per second. So that's what the first part told us to find. Now, using the mean values theorem, determine that somewhere during the acceleration, the speedometer shows the same value. So what it's saying here, because the mean value theorem is this, whenever you're asked to find something and it gives you a name of theorem or something, write that theorem down, or write the formula that comes in that theorem. You have to have a starting point. So what it's asking is the acceleration, is the rate of change somewhere between there exactly 44 feet per second? Has to. It just so happens at the end point. because that's where this came from. We started off at zero. It's faster than zero. And so as it accelerates, it's continuous acceleration. It matches this at the endpoint. So yes, that's how we use. C equals 8 seconds. When does it equal 44 feet per second? When the time is 8. Okay. Example 4. These are more physical interpretations. Example 4. Find f of x whose derivative is sine x and whose graph passes through the point 0, 2. So here's your solution. What's my first step? What's the first thing I have to find? Yeah, find f of x, whose derivative. So let's see whose derivative gives us sine x. So what function would that be? Close. Negative cosine x. Plus some constant. Any constant derivative is 0. So here are the point. It has to go through this point. So when x is 0, we have negative cosine of 0 plus some value of c. What does c equal? This thing has to equal 2. So negative cosine of 0 plus c. What is the cosine of 0? So it's negative 1 plus c. C is equal to 3. So therefore, the function that we just found is negative cosine x plus 3. Is that the only function? No, we could with trial and error, we could find another one that gives us the same derivative as sine. Finding velocity and position from acceleration. So let's look at a falling object. the acceleration of a falling object with time. What is it? This is of a falling object. Well, yeah, what's the speed of gravity? 9.8 what? Second or second squared? Positive or negative? Doesn't matter because it's a relative position. Since we're looking at down, we're saying it's positive. Opposite would be going up. Okay, so let's find the velocity from there. So what we're looking for here, this is the first derivative. Remember, acceleration is the first derivative of velocity. It equals to 9.8. So what velocity, what function would give us 9.8 t plus some value c? Because why do we put a plus c in there? Because we don't know, there's always a constant in there. Why is it 9.8 t? Because the derivative of this would give us 9.8. The c goes to 0, the t disappears. So it gives us 9.8, which is acceleration. So what is c? How do we find c? What point do we know we go through? What's the only point we know? Yeah. 0, 0. Because it's a falling object. So at time, this is time, this is your velocity. So velocity at time t, or this is my y value, I have 9.8 times t plus c. So when t is 0, I get 9.8 times 0 plus 0 plus c. So the velocity at 0 is equal to 0. So 0 equals c. Remember, this is my y value. There's my y value. So my equation for my velocity is 9.8 t. How do we find a position function? Remember, the position function, the first derivative of the position function is your velocity. So this equals my first derivative. What function could I use that when I take the derivative of it, I get that plus c? Remember, let's look at t. What has this is at the end of the derivative, you got t. So what happened first? Where did t come from? What did it have to have? It had to have a t squared. So the derivative of t squared would be 2t. So there's the t. So 2 times something will give us 9.8. 2 times something. So the position function is 4.9 t squared plus c. And same thing again, the only point we know for sure is 0, 0. So my y value so my position function would be 4.9 t squared. Because this is we have to start thinking this way more so because the next chapter deals with nothing but this. We have to go backwards now. But we also have to know now if y equals x to the fifth, where did that come from? There had to be something before it. So we know the earlier one before this had to have x to the sixth. And when I put it down, it disappeared because I don't have a six anywhere. So we'll talk about that in chapter 5, but that's what we have to start thinking about. The last thing we have in this section here are the laws of exponents. It goes from the algebraic aspect. If you have the same bases, what do you do with the exponents? Add them, right? So it works the same way here. E to the x, e to, well, x1, I can't use y, x1, x2, which will give us e x1 plus x2. If I'm dividing this, as long as the bases are the same, if I'm dividing, what do I do with the exponents? I subtract them. So the same goes with the exponential function. If you have a negative exponent, what does that mean? What does a negative exponent mean? What's that? Reciprocal, yes. Yes. All it means is since it's over 1, flip it and drop the negative. Even if we had something like this, 3 to the power negative 2, x to the fifth, y negative 6 over z negative 2. If it's got a negative exponent, it goes on the other side of the line. That's a negative, so it goes down. Only thing you do is drop the negative. That's what that rule says. So if you have a negative exponent, it simply means we take the reciprocal of it. Power raised to a power. You do what? multiply the exponents. Very good. So we do the same thing here. Multiply. If you have a rational expression raised to a power, what do you do? Yeah, distribute. What would this one become? X to the n, distribute there. And here I have e to the x to the power n, which means I would multiply. Because I have a power to a power. And lastly, if you have a product inside there, just distribute the exponent. What would the answer be in this one? Yes. Right. 2 to the power n. A lot of students forget that just because it's a constant, everything gets distributed. Right. That does it for that section. Pretty short and sweet. Let's look at the next section.